Hello everybody and welcome back. Root Beer here with more of the University of Waterloo's 2001 Euclid paper. That's the grade 12 level contest, the big scholarship contest. And yeah, we're on to question number 9 here. So hopefully you've had a chance to look at it. Question number 9, question number 10, they're usually very difficult. So we'll see what we can manage here. So triangle ABC is right angled at B, just as we have shown here in the picture, and has side lengths which are integers. Okay, so I'm starting to think of Pythagorean triples: 3, 4, 5, 5, 12, 13, 8, 15, 17. These are the things that just immediately run through my head at this point. A second triangle, PQR, is located inside triangle ABC as shown, such that its sides are parallel to the sides of ABC, and the distance between the parallel lines is 2, just as they have drawn in here. Determine the side lengths of all possible triangles ABC, such that the area of ABC is 9 times that of triangle PQR. Okay. So, So we want the side lengths, so we're looking for the Pythagorean triples of side lengths. So it might be a good idea to draw ourselves our picture and give some these side lengths some names like ABC or XYZ. So let's draw ourselves a picture and see what we can see. We're told in here that we are parallel. Okay, and we have a distance here of 2, 2, and 2. And I think this was A, this was B, and this was C, and I think they labeled it PQR. I'll check in a moment. But let's give some names. How about X, Y, and Z? Okay. And we'll just double check. Yep, PQR that way. Okay. So we're told that triangle ABC is 9 times triangle PQR. I don't exactly see how that's going to help. But I know that PQ, for example, is parallel to AB. And QR is parallel to BC. And PR is parallel to AC, although that one doesn't look as helpful. So in the corners here, we have some parallelograms. In fact, this one down here with B and Q is going to have to be a square. And then we've got some weirder shapes here. They're all trapezoids because QR is parallel to BC. Okay. And inside we've got a triangle here. Let's see if we can work out some of the angles. So I know that, well, we're not going to get any actual numbers for the angles. But I know I've got a right angle here and a right angle here. I've got more right angles really everywhere. Right angles. If I call this circle and this one little check, I know that dot plus check is going to have to be 90 degrees, but so QR intersects AC and is parallel to BC, so this is also going to have to be check. This one's also going to have to be dot. And this is going to have to be, this is going to have to be dot. This will be check. And you know what? This will be check, and this will be dot. So actually, PQR is going to be similar to ABC. So let's write that down. So since PQ is parallel to AC, so we'll extend PQ to hit AC at D, I guess. Then angle CAB is equal to angle CDQ. And since PR is parallel to AC, then angle CDQ must be equal to angle RPQ. So then angle CAB is equal to angle RPQ. Similarly, angle ACB must be equal to angle PRQ. And so triangle ABC is similar to triangle PQR. Okay? Now that's helpful because we also know that 9 times triangle PQR, 9 times that area is equal to the area of ABC. So since they are similar, there's a common ratio. So that AB is equal to RPQ, AC is equal to RPR, and BC is equal to RQR. But the area of ABC, because it's a right angle triangle, AB and BC are the base, the height and base. So it's 1/2 AB BC. And area of PQR, well, it's going to be PQ times QR divided by 2, base times height divided by 2. So 1/2 of AB times BC is 9 times 1/2 of PQ times QR, but AB and BC can be written in terms of PQ and QR. So RPQ times RQR. So we can cancel those guys out, cancel out the halves, and we're left with R squared is equal to 9. So R is equal to 3. Okay? We could have seen this another way if just by realizing that 9 is 3 squared. If you triple the lengths of an object, you multiply the area by 9. If you triple the length of an object, you multiply the volume by 27. So if you, just in general, stretching lengths by factor of R increases the area by R squared, the volume by R cubed. If there were 4-dimensional volume, it would be by R to the 4th. This is just a general fact. Okay. So that's just a general fact that I feel like mentioning at the moment, because it probably would have been a quicker way of figuring this out. So we know that we're stretching by 3. And in our original diagram, which I think I might redraw in a moment, we gave names x, y, and z to these lengths, so now we know the lengths of P, Q, and R. So Z, X, Y. So we're going to have Z divided by 3, and Y divided by 3, and X divided by 3. Alternatively, we could have given the PQ, QR, and PR names, and if we called them ABC, we would have had 3A, 3B, and 3C be the side lengths of triangle ABC. But we're asked for the integer side lengths that make up A, B, and C. That's why we gave them the names. Okay. So, what do we want to do here? We're missing a little bit of information here. The distances here are 2. And I think I mentioned a little while ago something about trapezoids. So let's get rid of the P, Q, and R because they just started cluttering up some space here. And let's draw in those trapezoids. We'll use orange. Okay, so we had a height for a trapezoid of 2 here, and here, and here. And we could make rectangles here, but I think if we connect just to the corners, these side lengths are parallel. So AC is parallel to PR, and so on. And we have heights of R, and we know the side lengths here. So triangle ABC, the area of that is the area of PQR. Plus these 3 trapezoids. Okay, so if we can figure out their area, which we can, because we know the height and we know the 2 parallel sides, we should be able to work out their areas in terms of x, y, and z. I think we'll be all set. So we know the 3 trapezoids have to constitute 8/9 of the total area. So if we know we have A here and B here, and we have a height h here, the area of the trapezoid is 1/2 h A plus B. Okay? Well, look at this base trapezoid here between Q, R, C, and B. We know that the 2 parallel sides are y and y by 3, and we know the height is 2. So we'll keep the trapezoid areas in orange. So we'll label them our first trapezoid, our second trapezoid, and our third trapezoid. So it's 1/2, the height is 2, and then we have x plus x over 3. And we'll leave a little space for the calculation there. For 2, we have 1/2, the height is still 2, and now we have y plus y over 3. And for 3, we have 1/2, the height is still 2, and the big base is z, and the small base is z over 3. So the 2's are going to cancel out, and we're just going to be left with 4x over 3, and 4y over 3, and 4z over 3. So the area of triangle ABC is 1/2 of xy, and that's going to be 1/2 x over 3 times y over 3, just doing the areas of ABC and the areas of PQR, plus 4x over 3, plus 4y over 3, plus 4z over 3. And it occurs to me I haven't used the Pythagorean theorem yet, so I can relate z back to x and y. We'll see if I need to. I'm going to multiply both sides by 18 to get rid of this 2 times 3 times 3, so we'll have xy here, plus 24x, y, and z. Okay. So, what else can we do? Well, we can bring the two xy's over together, so we get 8xy is 24x plus 24y plus 24z. I guess we can divide by 8. xy is equal to 3x plus 3y plus 3z. And now I think it might be a good time to substitute in something to get z. Well, let's get z on a side by himself. So xy minus 3x plus y is going to be 3z. So let's square both sides, and we'll be left with 9z squared over here. And I don't know whether I need to square this yet. But z squared is equal to a squared, or x squared plus y squared. That's by Pythagoras. So if I use binomial theorem on this side, x squared y squared minus 6xy x plus y plus 9x plus y all squared should be equal to 9x squared plus 9y squared. Alright, has that actually helped me, or is that maybe just a giant mess? Let's continue expanding some stuff out, and maybe we'll group everything. I think we'll get a relationship between x and y in a moment. xyx minus 6xy squared plus 9x squared plus 18xy plus 9y squared is equal to 9x squared plus 9y squared. Well, those are going to cancel out, and I think everything is going to have a factor of xy. Let's just make sure. Yeah, so I can take out an xy everywhere. So xy minus 6x minus 6y plus 18. Now this thing here in the middle, it really, really looks like I could factor it in some way. So have we used every piece of information? Distance between the parallel lines is 2. That gave us the height of the trapezoid. We know that we're going to be shooting for integers. And we've used the fact that they're right angles to get us to eliminate z. I think we're all set. We just need to sort of figure out what integer values of x and y solve this mess. So I have a product here equaling 0. That means one of the factors must be 0. It can't be x, it can't be y, because these are the side lengths. So we must have xy minus 6x minus 6y plus 18 equal to 0. Now, it looks like I could factor this. I want something times y minus 6 here. And it's got to be minus 6. But then that would be, I'd need to have minus 6 times minus 6, that's plus 36. But I have only plus 18. So, in order to get this expression here, which I want, I'm going to add and subtract 18. Or I guess just add 18 to both sides. So that's xy minus 6x minus 6y plus 36 equals 18. And this I can factor as x minus 6, y minus 6 is equal to 18. Okay, now we're cooking. Because we have an expression in terms of x and y, nice easy numbers here, equaling 18, and I can list out the factors of 18. So since x and y are integers, then x minus 6, y minus 6 must also be integers. So, because if you subtract two integers, you still get an integer. So they are integer factors of 18. So what are the factors of 18? Well, we've got this, since it's got to be integers, we can have pairs here. Minus 18 minus 1, minus 9 minus 2, minus 6 minus 3, minus 3 minus 6, minus 2 minus 9, minus 1, minus 18, and then the positive ones. I don't think we'll be using these negative ones. I don't think there's any that are small enough that would work. Then we get 1, 18, 2, 2, 9, 3, 6, 6, 3, 9, 2, and finally 18, 1. These are the integer factors of 18. Usually we only do positive integer factors, but I'm not taking any chances here. So if I let so these are my factors, integer factors. So I'm going to take these, we'll say they're a, b, and I'm going to say let a equal x minus 6, and b equal y minus 6. So really I just need to add 6 to both the numbers here. So minus 12, 5. Well, that's not going to work. Minus 3, 4. 0, 3. 3, 0. 4 minus 3. 5 minus 12. 7, 24. Ooh, that looks promising. 8, 15. That one also looks really good. 9, 12. And then we have 12, 9. 15, 8. And, of course, 24, 7. So these ones are out. And we'll just explain why. So the side lengths need to be positive. So we have 6 pairs here. Really, we only have 3 because we sort of doubled up. So the possible shorter non-hypotenuse side lengths of ABC are 9, 12, 8, 15, and 7, 24. So now what we need to do, these are our possible x and y, but remember we still need z, and we need z to be an integer as well. Okay? So we're not done yet. So z squared is x squared plus y squared. So 9 squared plus 12 squared. Well, that's 81 plus 144. And that should be 225, which is 15 squared. So z is 15. Or for the second one, if you know your Pythagorean triples, you're going to be okay. 64 plus 225. It's 289, so that's 17 squared. And the last one, z squared, x squared plus y squared. You know all these are going to work out if you know Pythagorean triples, but suppose we didn't. We still need to make sure that each z is an integer length, because maybe there's one pair where z isn't an integer, and we ask that every side of ABC is an integer. So 49 plus 576, that's going to be 625, which is 25 squared. Z is equal to 25. So ABC can have side lengths 9, 12, 15, 8, 15, 17, and 7, 24, 25. Okay? So I'd be tempted just for a moment to think, well, we had this minus 12 and this 5 here, and this minus 3 and this 4. And could we have maybe had 5, 12, 13 somehow, or 4, 5, 3, 4, 5 somehow? So I'm just going to review the questions, make sure that that couldn't have happened. So what did we do? We did a lot of work, actually. So I'm flipping back through a lot here. So first we used some angles to realize that PQR needs to be similar to ABC. So I don't really dispute that. And we figured out the ratio between the side lengths is going to be 3. We could have done that quicker than we did, but that's okay. And then we realized we can break it up into these trapezoids. I wonder how the problem would have changed if I'd gone with the original way I broke up the triangle, which was getting that little square down there with BQ, so that'd be a square of side lengths 2 and everything. Still would have had a summation calculation to get the area of ABC in terms of PQR and some other things. Some trapezoids and some parallelograms, but I think the way we did it was fine. Let's see. So we worked out the area of our trapezoids. Everything went smoothly. We just had to manipulate that equation to a point where we plugged in z squared. And that gave us that x minus 6 times y minus 6 needs to be 18, and there is no getting around that. And since we need to have positive integers, I think that's it. I think it's just the 3 solutions. And each one worked out. So 9, 12, 15, 8, 15, 17, and 7, 24, 25. Those are the only possible side lengths we could have here. I guess if you had something like 3, 4, 5, it would be way too cramped. PQR would be way too small. Maybe it'd be fine. But No, I'm confident in the way we handled that question. Okay. So 3 possible answers there. That was an excellent question number 9. I did get stuck a little bit there. Took a moment to think of how to break it up with those trapezoids in a smart way. And I certainly got stuck for a moment trying to get that last expression, xy minus 6x minus 6y plus 18, to make that into something useful. But it all worked out, and we made a nice list of the integer factors of 18. And from there we got our solution. So good question overall. And I can't wait to see question number 10, but we'll both have to wait for that in the next video. So I'll see you guys for question number 10 on the 2001 Euclid paper next time.